Now, a third example, actually this is not an example, but an application if you want. It's a note on work. Okay. Well, from physics, we recall that work is force times distance. You are familiar with this formulation. However, here there are certain restrictions. What are the restrictions? In the first place, okay, we have a straight line, a trajectory. We have a point mass, m. We have a force, okay, in the direction of motion, so it's parallel, and in the same direction. And under this force, this m moves a distance d. Okay. Then, okay, the force is F times d. Of course, F is constant. So, again, if F is constant and the body moves on a straight line and force acts in the direction of motion, then this formula is the basic idea of work. Now, in general, we don't have it, obviously. What do we have? Firstly, okay, in general, the body moves on a curve, not on a straight line in general, all the time. And the force, okay, is not constant. Namely, okay, it is changing from point to point. Okay. And thirdly, the direction of the force is not, okay, parallel to the direction of the motion. Is not the same as the direction of motion. So, we have the following picture. Okay, we have a curve, C. We have a body moving on the C. At some point, okay, the body is moving, of course, we have a tangent here, and we have a force. If this is the point, xy. And the force is not in the direction of motion. There's an angle between them, okay? And the question is, what is the work done? If the body moves from this point up to this point on C. Well, as we usually do with applications of integrals, we consider this, okay, by taking a very small portion from pi minus 1 to pi, and then here consider this movement. Now, when the body moves from here to this point, okay, under a force, the force is something like this. It is a vector, okay, because its direction changed from point to point. And in this movement, which is our delta D, okay, here we can assume the following. First of all, we can assume that the distance moved, that is delta d, is on the tangent line. Because if delta d is small, the tangent line, which of course is almost the same as the curve, if delta d is small, we can assume that it is a distance on the line, almost. And okay, we can assume that force is constant. Force does not change. Actually, it does not change much. Certainly it changes, okay, on or during this movement, during this motion. Okay, so we are almost inclined to use the formula directly, but still we have a problem. Well, f does not change much from here to here. Namely, if this is our f at this point, it's again the same f at the point pi. However, the direction of f is not in the direction of motion. So still, okay, f is not in direction of motion. So we can still not use the formula. So what happens is we have to take the component of f, okay, along the direction of motion. Okay. So here, the tangent vector to the curve. So what we do now, we have a vector f which points an irrelevant direction, but we have to take its component in the direction of motion, which is the tangent vector direction. Okay, so okay, we take f dot product the tangent vector, so it would be x prime ty prime. Okay, but this does not give the component. To get the component, we have to take the projection, and in the projection, okay, let me put here that this component means actually projection. We have to divide this by the length so that it's a unit vector. Okay. Well, this is nothing but our normal vector. So what happens? So delta work is, okay, we can use the formula now. The function, which is f dot n. Now this function, this force, is in the direction of motion because we took the dot product with n times, okay, delta d, which is of course delta s, because delta d is a part on the arc which we identified with the length on the tangent line, so that we could use the formula. But then the work total would be the limit of the sum of f dot n delta s. In other words, it would be the line integral f dot n ds. So, in the most general formulation, when f is a vector, its direction is not in the direction of motion, the body moves on a curve, and f is not a constant vector, and all that, okay? This is the work done. Actually, this is taken as the definition of work. So this is work. So this vector formulation of the second type of line integrals, okay, gives us directly the work done in the most general formulation. Well, we can say a little bit more about this. Okay. Let us now, okay, consider the following. Recalling the second law of motion of Newton, okay, in vector form, it is the force is m times the vector a. Well, what is the vector a? As we considered it, it's the derivative of velocity, or if you want, it's the second derivative of, okay, x of t, y of t, which is distance, okay, from 0 to the point. So this is the position of the body. So the second derivative gives us the acceleration. That's Newton's second law of motion. Here, of course, both f and a are vector valued functions, as we see from here, and they depend on x's and y's. You can do the same thing in space with x, y, z. I will not go into that, but it's exactly the same. Well, so what do we get? The work done is f dot n ds. So far, okay, we know it, everything is fine. But that happens to be, okay, remember f is n times a, so it's n times the derivative of the v of t dot, this is f, the force, dot n. Now, what was n? N was the derivative, okay, divided by the norm, the length. Okay. And then, of course, we had ds. Okay. Now, looking at this part only, we have m, the derivative of v of t, dot, okay. Now, this n is actually the derivative of x of t, y of t, so it is v of t divided by length of v. And we have ds, etc. Well, maybe I should go one step further. Okay, ds is nothing but length of v of t dt. Okay, if you open it up, okay, you will see that you have exactly that, because this is the square root of x prime t squared, y prime t squared. Okay, but so we will be concentrating ourselves on this. Now, let that stay there. Let us take the derivative of length of v squared. Now, this is a vector norm squared, so it's the derivative of v of t dot v of t. Remember from vectors, whether you have dependence on t or not, the dot product of a vector is the length square of the vector. Now, we remark that the dot product obeys the derivative rule for products, and so it's the derivative of v dot v of t plus v of t dot the derivative of v. In other words, it's 2 times v prime t dot v of t. Well, what do we have here? We have the derivative of v dot v. So exactly this one. In other words, okay, with this formulation, I can continue with what I have over there. So that would be, I'm continuing with the integral over there. The integral over c, okay. Yes, maybe I should say from a to b now in formulation. I would have here 1/2 of the derivative of v of t squared. Okay, I can write this instead of v prime dot v. Well, what else do I have here? I have an m, okay, and the rest is just dt. Now, this tells me the following. Okay, so it is 1/2 m. Now, the remaining part is the derivative of a function of one variable, which is a scalar. It's not a vector anymore. We have the length squared. So, if you take a function of t, a scalar valued function of t, something like f of t, if you have the derivative and then you integrate, well, you get the same thing back. In other words, this is exactly the length of v of t squared from a to b. Okay. When we take a closer look at it, we see that it's 1/2 m, the speed squared, which is defined in physics as kinetic energy. So, the kinetic energy at the end minus at the beginning is the change in kinetic energy. Okay. So, okay, work done is the change in kinetic energy. So we prove this in the general formulation. Okay, now a final example will be the following. You can regard this as an application to work. As my fourth example, let I be the integral over c y dx plus x dy. Okay. And now I will assume different cases. C is, say, a unit circle. Okay, you can assume counterclockwise oriented. Okay. Then, I would be, well, firstly, a parameterization, of course. We are familiar with it by now. I will not spend much time on it. T starting from 0 to 2. Well, this is counterclockwise orientation, so check the orientation. Then I becomes, okay, y dx sine t minus sine t plus x dy, which is cosine t, okay, from 0 to 2 pi dt, of course. Now, this tells us that we have cosine square minus sine square, okay, which is cosine 2t. That's not important. Well, integral of cosine 2t is sine 2t. At 0 and 2 pi, of course, it gives 0. So this is cosine 2t. Integrate, put the values, you have 0. Let C be, say, the unit square, counterclockwise oriented. Okay. We will integrate over C, but we have 4 parts, so let us calculate them one by one. On C1, well, what is C1 after all? C1 is where y is 0. So, on C1, y is 0, and exchange 0 to 1. It's a parametrization, a very simple one. Now, when y is 0, you have 0 dx plus x. Now, dy, because y is constant and 0, this time dy is 0. So the integral is 0. Now, calculate over C2. Well, C2 is when x is 1. Okay. And y is the parameter. So a formulation would be 1, y. Y changed from 0 to 1. This is C. So write this, okay, from 0 to 1. Well, y is a variable, okay, but x is constant, so dx is 0. Plus x times dy, well, x is 1, and dy is dy. So it is 1. On C3, okay? Well, on C3, first of all, y is constant and 1. It's constant. So we can formulate C3 very easily. Namely, it is of the form x1, and x changed from 0 to 1. Well, at 0, we are at this point. At 1, we are here. So the direction is opposite. So this is minus 3. Okay. But we can use it for our formulation. Namely, we have here minus C3 of y dx, y is 1, dx is dx, plus x dy. Well, x is x, but y is constant. So dy is 0. So this tells us that we have minus dx, and in the formulation of minus C3 from 0 to 1. So it's minus 1. And finally, let me just do it here, integral over C4. Well, on C4, x is 0 and constant. Well, if x is 0, dx is 0. Okay, x is constant after all. And because x is 0, whatever dy is, we always get 0. In short, integral over c of x dx plus y dy is 4 zeros, 0, 1, minus 1 plus 0, so it is 0. Okay, is this coincidence? Well, there are no coincidences in math, of course. You can, just to be sure maybe, take C as the same integral still to be a triangle of this for a change. Okay. Now on this, calculate actually and show that integral C of y dx plus x, sorry. Did I do it correctly all the time? That should be y dx. So C1 is correct, C2 is correct, C3 is not. Actually, we have a change here. No, y is 1, so this is correct. And this one, y dx, so that is correct. Only this one is not correct, but that's not important. Okay. So you can show that this is 0 as well. So the question is, okay, is this coincidence? Okay. The answer, of course, is a big no, because we have a nice theorem. Called Green's theorem, which we will not consider in detail at this point directly, but just let me say what it says. It says that under certain conditions, if C is closed and R is the region bounded by C, then it says that the integral over C is the same as the double integral of q sub x minus p sub y dA. Okay. Well, notational thing. Usually we put a circle here, and it just means the following. If C is closed, one usually puts a circle. Okay. This means C is closed. Okay. Just a notation, nothing particular about it. Well, what does Green's theorem say in this case? It says the following. You take the derivative of q with respect to x. Well, in our example, p of xy is y, q of xy is x. So, q sub x is p sub y. They are both 1. Which means that right-hand side is 0. So, This is 0. For any closed nice C. Okay. And here C is not important. It can be a circle, it can be a square, it can be a triangle. All these integrals will be 0. If it's an ellipse, still it is 0, and so on. Well, a last remark. In Green's theorem, or rather in vivo Green's theorem, okay, Q sub x and P sub y, okay, must have a significance. Actually, even the difference must have a meaning. What is that? Okay. Why would this be important? For example, why don't we have P sub x minus Q sub y, or whatever that comes to mind? Well, it does. It does have a very important significance. Okay, this will be the topic of our next considerations. Okay, and we will start from this point on.